Hello class, welcome to today's lesson, which is about the second derivative and the concavity of a function. I already told you to investigate these two concepts in depth, not just superficially. So this is just a brief summary of what you should have done already. Okay, so first of all, what is the second derivative of a function? For example, let's suppose I give you a polynomial function. Let's suppose I give you 3x to the 4 minus x to the cube plus 2x squared minus 5x. Okay, let's keep it right there. Okay, so we know how to differentiate one function like this, and the first derivative is equal to 12x to the cube minus 3x to the square plus 4x minus 5. You should be doing this already quite naturally and with some familiarity, okay? Okay, perfect. So this is what we knew before as just the derivative of this function, and that's also still correct. But in the context of speaking of higher order derivatives, like the second derivative, the third derivative, etc., then we have to add to this derivative, we have to add the adjective of first derivative. So what we knew before as just the derivative is now the first derivative. Now, if you take now this function, and you should understand that the derivative of a function, this is my original function, the derivative of a function, this thing is itself a function, right? Which can be differentiated. So let's do it. Let's differentiate this function. We're going to write one more time the f, and we're going to write two times these little symbols, the prime, f prime of x, and now this is read as fb prime of x, or just the second derivative of x. I'm sorry, of f. Okay, and we just get the derivative of all of this. That's going to be 12 times 3, that's going to be 36 x to the square minus 9x plus 4, and the derivative of this is 0, so there you go. This is the second derivative of what function? Of my original function. You see? That's how it works. And of course, this is the first derivative with respect to this function. You see how it works? Okay, so that's basically, with just one example, I think you can get the idea behind the second derivative. And you can go further, right? You can get the third derivative, the fourth derivative of a function, etc. Okay, so that's all about the second derivative. There's nothing much else to say, at least not in this course. Okay, now let's talk about the concept of the concavity of a function. Surely you remember from your second semester and your third semester that we talked a lot about parabolas. You know, the parabolas is one of those functions that are very studied for various reasons. You know, they come up quite often in mathematics and in physics. And we basically had two types of parabolas. Ones that look like this, and ones that went like this. You see? Basically, ones that opened, that's one of the common words employed. Open, well, open upwards, like so. And ones that open downwards. Okay? I'm gonna draw more of these. For example, this one also open upwards, this one, and here this one open downwards, this one too, this one, etc. Okay, very well. There's another word for this feature, and we say, instead of opening the upwards and opening downwards, we say that these parabolas are concave upwards, and we say that these ones are concave downwards. Okay, this is visually what it means. Visually, I'm still not telling you in very formal terms what that means, but just visually, that's what it means: concavity upwards and concavity downwards. And the same adjectives or the same property can be related to any other type of function. For example, what if I draw something like this? For example, I'm gonna draw something resembling a cubic a cubic function. By now you should be more or less also familiar with these types of functions. They look a little like this in most cases, and then they go downwards infinitely and upwards infinitely, or the other way around. They come downwards and they go like this and they go this way. Okay, either way. Okay, so look at this function, guys. I want you to look at it. Remember that these are called the turning points. Can you remember that? These two fellas right here, turning points, in which you go from increasing behavior to decreasing, 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 and then increasing again. Okay, so these are my turning points. But now I want you to pay attention to another very distinctive point, which should be more or less over here. Okay, I'm not gonna yet pinpoint it. I'm just gonna tell you that it's somewhere over here. And that point is distinctive because you can see that the following is happening. If you notice, the function, when you come from minus infinity, the function is going like in this way. It's increasing, 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 increasing. Okay, perfectly. And then it goes like this. And then more or less at about this zone, somewhere over here, what you have is that the concavity of this function, the concavity changes. Can you see how in this region, and I'm gonna signal that by a specific color. I think that's gonna help. You know, I'm just gonna overlap the colors. I hope it doesn't look so bad. So if you notice over this section, all of this, at about up until more or less over here, this part of the function seems to look, or pretty much looks like a parabola, which is concave downwards. Can you see? Concave downwards. And from this point uh, upwards, what we have is the other type of concavity. We have concavity upwards. I think I don't know what I said here. I must have said concavity downwards. If I said that, that's fine. I can't remember. I didn't sleep so well. Okay, and in this other part over here in red, the concavity is upwards. Concavity downwards, and from here onwards, concavity upwards. So you see, so that's enough information or enough particularity in order to say that this must be a special type of point, because it's how can I say this? It's a point in which the function changes some sort of behavior. In this case, this point is signaling the change of behavior in the concavity from concavity downwards to concavity upwards. And it's pretty much in that context, it's a lot like your turning points. Remember that also the turning points, let me write T for turning points. And I'm going to tell you in a moment what this is called. In that context, the turning points, at the turning points, your function also changed some sort of behavior. In this case, whether it was increasing from decreasing or vice versa. And again, at this point, what is happening is that the function is changing its concavity. Perfect. So what do we call this point? We call it, in mathematics, we call it an inflection point. Punto de inflexión. Inflection point, which is a point at which your function changes concavity, or also it's known as curvature. Curvature. Okay, so perfect. That's what an inflection point is. That's what it is. Remember, don't memorize the definitions. I'm actually not writing any definition. I'm just explaining to you what it is. If you understand what it is, you don't have to memorize words. You can explain it in your own words. That's the best thing you can do. That's when you can tell that you're learning or not. Okay, so these are the inflection points, and our task in this lesson and in the next one maybe will be to find these inflection points, to find those points at which any function whatsoever changes its concavity. Very well. Okay, now, if you remember, guys, how did we find, well, here we go. Can you remember how we found the turning points? We found them by using what? The first derivative, right? This little thing right here. If this is our function, f of x, then by obtaining the first derivative or just the derivative of this function and making that derivative equal to 0, we could find these two turning points. In this case, we have two. There can be many more, etc. Okay, now something similar is going to happen in order to find the inflection point. What we have to do is get the second derivative of my original function, you see, make it equal to 0, solve that equation, and then that equation is going to tell me, okay, your possible inflection points will be so and so, and that's it, guys. That's how you do it, or that's the process that you have to that you have to do in order to obtain the possible inflection points. Do you remember that when we did this process over here, the first derivative, in order to find the turning points, I always said this process will tell you the possible turning points, Then you have to actually do something else in order to find whether they were in fact turning points or not. Well, it's going to be the same with the second derivative. What the second derivative will tell you by doing this process is just the possible inflection points, possible turning points, and possible inflection points. Okay, and that's what we're gonna do right now. Okay, I want you to look at, I already have some functions graphed. Okay, I want you to look at this function, guys. Maybe we're just gonna do one or two of, I have 4 functions, and I don't want to have a very long video, so maybe we're gonna do one or a couple of them, and then in another video, part 2 of this lesson, I'm gonna give you the rest of them, the rest of the examples. Okay, so let's begin with this function. Again, it's a cubic function. It's f of x equals x to the cube minus x squared minus 4x. It looks like this. I'm gonna zoom out. You see? I'm gonna zoom in. And just visually, we can understand that somewhere over this zone, there seems to be an inflection point, because it's pretty clear that my function over, one more time, let me use the colors. Let me use, okay, blue is fine. It seems as though over this zone, all of this part of the graph, up until about here, okay, we can see quite clearly that it's going with a concavity downwards, and from about here, more or less, we can see that the function has a concavity upwards, and it's gonna remain like that for the rest of the function. You see, so it's somewhere over here, somewhere over here, which is at about, if we estimate the value of x at that point, uh, this is 2, this is 1, it should be about zero point 0.5, more or less. So we know just from the graph, we know that the inflection point must happen somewhere at about x equals 0.5, more or less. Let's see if that's true. Let's see if that's true with analysis. Okay, remember we have to have analytical methods of doing these things and not just visual methods. Okay, so let's go back to the blackboard. Okay, and now let's get to work. So what do we do in order to find a possible inflection point? Okay, this was my function, the same function I had on Desmos. I'm gonna write it here. I said that it was equal to x to the cube minus x squared minus 4x. So this was my function. Let's call this function 1. Okay, so what do we do first? Well, let's write the goal. Let's write the goal. The goal is finding the possible inflection points and tell in what intervals f is concave upwards and in which it is concave downwards. So big goal, concave downwards. You always have to have your goal clearly in your mind, okay? Because sometimes people start doing stuff and they don't really know what they're trying to get at, okay? So this is my goal, finding the possible inflection points, and with these inflection points, help myself in order to tell in what intervals f is concave upwards, or like this, and in what intervals it is concave downwards, like this. Okay, let's do it. Steps. Number 1, get the second derivative of this function. And in order to do that, you first have to get the first derivative, obviously. So this is my original function. Then this is my first derivative. Minus 2x minus 4. And then my second derivative of or fb prime. Fb prime is going to be 6x minus 2. There you go. This is my second derivative. And that's the first thing I need to do, getting the second derivative. Okay, what's next? Let's continue over here. Okay, second step. Make fb prime equal to 0. Okay, so this is my second derivative. I'm gonna write, well, I don't have to write down the f anymore. I just have to write down this part because this is my second derivative. And I'm gonna make it equal to 0. And one more time, this is a question that I'm asking mathematics. I'm kind of like asking, try to give me the possible inflection points. And the way to do it is I have to solve this equation. It's a very simple equation. We get 6x equals 2, and then x equals 2 over 6, which is 1/3. 1/3. Okay, so this is what I was trying to get. This is my first part of the goal, finding the possible inflection points. We're done. Okay, this little thing in here, the underlined command or instruction, it's this. Okay, so I'm gonna frame it and I'm gonna actually write, okay, like possible inflection point, not necessarily an inflection point, but it's possible. possible inflection point. Okay, now and if you look, guys, if you remember, or if you go back to the previous topic, it looks a lot. This whole process looks a lot completely. It's completely analogous to what we did with the first derivative and the turning points. It's basically the same process in abstract terms. Okay, now number 3, find in what intervals. Well, yes, fine. Find in what intervals f is concave upwards and concave downwards. And we're gonna use, one more time, we're gonna use this point, this particular point, this possible inflection point. Okay, one more time. What I'm gonna do is I'm gonna divide my x-axis. You know, if I'm gonna draw it over here, this is my whole x-axis. This is my y-axis, and this inflection point, this possible inflection point, divides the whole x-axis in two parts, right about here. If we think that this is 1/3, if we locate 1/3 here, then this number, which is this, divides the x-axis into two parts, from -infinity to 1/3, and from 1/3 to infinity. So basically we have two intervals. Interval 1 is from, I said, from -infinity to 1/3, and that's interval number 1. And the interval number 2 is from 1/3 to infinity. And if this is in fact an inflection point, my concavity has to change at this point. Okay, so either your function is completely concave downwards in this section. Okay, that's what I'm trying to trace here. Try to look concave downwards and then concave upwards at this point, or the other way around, concave upwards in this section from -infinity to 1/3, concave upwards, and then concave downwards. And how do we tell? How do we tell? Well, you're gonna use one more time the second derivative, and you're gonna evaluate your second derivative in any point to the left and to the right of your possible inflection point. So choose whatever you want, it doesn't matter. Choose simple numbers. So if you choose 0, that's the simplest number, right? Because when you choose 0, a lot of things go to 0, and it's very simple to evaluate. So I'm gonna choose x equals 0 and x equals 1. One number to the left and one number to the right of this possible inflection point. So over this interval, I'm going to evaluate the second derivative in 0. So fb prime of 0 is going to be equal to 6 times 0 minus 2, and that's going to be equal to minus 2. And one more time, we really don't care about the number. In this case, it was 2. We don't care about that number. We care about the sign. It was negative. Okay? And let me tell you what that means. When the second derivative is, when the evaluation of the second derivative is negative, what that means is that your function over this zone in which you evaluated from in this region, in this part of the whole x-axis. What that means is that your function will be concave downwards. Concave downwards. In other words, it's gonna look like so, like that. Okay, so we know about that. We are 100% sure about that. Now let's evaluate in the other point to the right of my possible inflection. Let me actually draw a partition over here. Right there. Now let me evaluate to the right of this imaginary line. Let me evaluate the second derivative. One more time, it's this thing. I'm gonna do it over here. So f b prime of 1, I chose 1. Any other number would have been perfectly okay. So f b prime of 1, and that's gonna be equal to 6 times 1 minus 2, and that's gonna be 6 minus 2, that's plus 4, or just 4. So basically what I found is that over this region, over this part, my second derivative is positive. One more time, we don't care about the 4. I only care that it was positive. And when I know that my second derivative is positive, what that means is that my function on that region, on that zone, on that interval is concave upwards. Or in other words, it's going to look like this, like that. Okay? So, conclusion. First thing is this: was this a possible? Was this an inflection point? This number, because remember, at this point, right at this point, it's only a possibility. Okay, now once you do this thing, and once you realize that in fact this point over here is the point at which your function changes concavity, then you are sure that it was an inflection point. Okay, it's no longer a possible inflection point, and now you are sure because concavity changed from concave upwards over this region. Let me try to draw that in white. We know that at this point, at this partition, the function will look like so: concave downwards, and right at this point, it's gonna look concave upwards. You see? Now, where exactly, like, is it gonna be like in this way, or maybe over here, like so? We don't know. You have more information, more information. You need the turning points, the zeros of the function, etc. This procedure only tells you that the concavities of the function. Now, that's the conclusion, guys. We have completely finished the task. Finding the possible inflection points. It's this one. It's 1/3, and we are sure about that. And tell in what intervals f is concave upwards. Okay, let me go here to my concave upwards. It's in the second interval from 1/3 to infinity. So it's from 1/3 to infinity. Over here, my function will be concave upwards. So I have completed that part, and in which intervals it is concave downwards. So let me see, concave downwards, it's over here in this interval from minus infinity to 1/3. So in this zone. So my function should look like this. Okay, now let's go back to the function, because we already have the graph of this function on Desmos, and it should look like this in regards to its concavities. Maybe it's not gonna look maybe it's not gonna cut the axis at these places, etc., but in regards to the concavity, it should look like this. And there you go. You see, we know now that the inflection point is 1/3, which is about 0.33. So it's about this one. You see, that point that I'm just clicking on, that is the inflection point. And as you can see, I'm gonna just remember this point. As you can see, it's first to the left of this point. To the left of this point, we have concavity downwards, and to the right of this point, we have concavity upwards. You see, was that our conclusion? Yes. Concavity downwards from minus infinity to 1/3, and concavity upwards from 1/3 to infinity. And so that's how it works, guys. If you see, if you can notice, the process closely resembles the previous process with the first derivative and the turning points. But now we're gonna use the second derivative, and we're gonna call this particular point in which the concavity changes. We're gonna call it the inflection point. But the process is completely analogous. You see, like it's like twin processes basically. Okay, how much time have I talked already? 30 minutes. Okay, that's enough. That's completely enough. Let me stop the video right here, and I'm gonna exemplify the three other functions in another video that you can watch at any time you want before Friday. Before Friday, this should be completely done before Friday, so that we can begin on Friday the next lesson. Okay, guys, so thank you so much. I hope you have understood. Any questions, please address them to me on a private message or some other way. And that's about it. Have a good day, guys.